Okay, off we go. So here's where we were last time. We had set up a strategy for computing a bunch of different things. The scenario we want to consider is that there's some quantity distributed over a surface. Let's be deliberately vague about what that quantity is. Maybe there's mass distributed over the surface. Maybe there's ants crawling on the surface. Whatever. Let's, again, deliberately vague so that this can be applied to anything. But the big strategy is let's cut it up into little pieces, on each of which, hopefully, we could talk about stuff per unit area times area, right? And then just add up over all those pieces. Now, how are we going to actually do this? Separate question. We'll deal with that momentarily. But just as a strategy for computation, this Riemann sum-like expression, we're going to take as our definition of something called a scalar surface integral. Okay. All right. Now, how to compute it? Well, we actually kind of already have everything that we need to do this. Recall, we've already talked about parametrizing surfaces. We've already talked about how a little piece of output area, ds, relates to a little piece of input area, ds dt. We've already computed this stretching factor that, what you multiply by that to get that as capital N, magnitude of capital N. That's our stretching factor. And so just insert that into the expression where you have your ds. ds is magnitude of capital N times ds dt. And everything else pulled back, and we have ourselves a double integral that will allow for computing one of those expressions. So you may notice this is very, very similar to what we did when we set up and did our first sort of computation of scalar line integrals. This is the same basic idea, just one dimension higher for surfaces. Okay. And good news, it doesn't matter how you parameterize. Parameterize however you like, all good. Okay, so let's see an example. Now this is another deliberately analogous to something we've done with scalar line integrals. We're going to set up one scenario, and then we're going to compute four different things. We're going to compute the mass and the couple of coordinates of the center of mass and the moment of inertia around a certain axis, etc. And you can see these calculations. There's four of them here. We're going to talk about two of them, and then the other two I'm going to suggest y'all fill in the blanks and read yourselves. So all of these, of course, are talking about the same mass distributed on the same surface with the same density. We're going to parameterize that same surface one way, and so our stretching factor is going to be the same for all four of these calculations. Okay? And again, you may recognize some of that anyway from chapter 6 as well. So now let's see here. We're talking about the unit sphere. That's how you parameterize the unit sphere. Now, specifically, we're only interested in half of that unit sphere, but we'll worry about that later as to which values of phi and theta are actually relevant to us. But certainly, the surface we're interested in is on the unit sphere, and so parameterizing the unit sphere is all we're going to need. And now, again, there is a calculation to compute the stretching factor. We have already done that calculation, or at least we've already waved our hands at it. Right? That was last time when we were, in fact, let me just scroll back to it. It was this calculation right here. We used the same parameterization. We computed the partials. We did the cross product. We took the magnitude, yada, 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 and sine phi was our answer. Okay. Make sure, again, fill in these blanks. Make sure you can do that. It's a lot of little details. And you gotta be able to functionally execute that. Okay, so let's talk about how to compute the mass. Whole is the sum of the parts. Right? On any given little piece, mass is mass per unit area times area. Here's a formula from the previous page. Area, ds, from the parameterization is going to be stretching factor times d phi d theta. We just got through computing that stretching factor right there. I mean, this integral's really coming together at this point. Now, there is one thing that is easy to forget. I've been dramatic about this a couple of times. Again, I find over the years, the more dramatic I am about certain points, the less I see those mistakes on exams. What do I do with that z? Don't forget that is in the parameterization. The parameterization is literally telling you x, y, and z as functions of your parameters. So z is cosine phi. And we've got our integral pretty much set up. There's one last thing we got to worry about, and that is the bounds. So keeping in mind that we're only looking for the upper hemisphere. Right, so we've got our sphere, our full sphere, but I just want just the top part of it, and I think you can probably see that that top part of it is for values of phi between 0 and pi over 2. Right? Any values of phi beyond pi over 2, you're getting into the lower half of the sphere. Does that make sense to everybody? Is everybody comfortable with that geometry? Okay, so that gives us those bounds for this integral. There we go. So phi going from 0 to pi over 2. And at this point, it is a double integral, and plug and chug. It's not even so bad. Everybody happy? Okay. All right, now let's do the second one. At least I'm going to wave my hands at the second one. The second one, we were interested in the x-coordinate of the center of mass. There's a pat formula from the end of chapter, let's see, section 5.6, right? If you want to know a given coordinate of the center of mass, it's always like this. Conveniently, we've already computed that mass here, right? So we don't have to do that over again. Let's see here. What are we going to do about this dm? How are we going to expand and simplify that dm? Well, good news, we already did, right? And all of this is going to be the same. dm. Oh, let's see. dm. I'm having vision problems here. dm is all of that. So likewise, all of that. I don't have to rethink all that stuff. It's the same scenario. Right? It's the same density, it's the same parameterization, so the same z and the same stretching factor. Everything's the same inside of the green. You don't have to do that all over again. All we have to do that's new is make sense out of x. And wait a second, what is x? Here it is. Again, the parameterization tells us x is sine phi cosine theta. So, there you go. Yeah.
Just look at why we got the z.
Do what now?
The first part. Why did we got the z?
Yeah, because that was the given density. Let's see if I can. I just want to get it on. There we go.
Okay.
Yeah. Oh, I'm sorry. And I may have failed to mention that, but yeah. Right. Is that satisfying? Okay. Okay, so you see how these calculations, it's pretty plug and chug, right? Just don't forget your stretching factor. Don't forget that your parameterization is what you're pulling back through. Said differently, don't forget your parameterization tells you how to plug in for x, y, and z. And off you go. It's pretty straightforward stuff. Okay, so new example. How are we going to generalize the idea of flux? Now let me remind you what we know so far about flux. There's our formula for it. The idea is that if the vector field in some appropriate sense represents how fluid is flowing, then flux in some correspondingly appropriate sense tells you the flow rate. Right? So quantity of fluid per unit time. Not velocity, not, linear distance per unit time like a speed, like the vector field might represent, right? But quantity of fluid, maybe volume or maybe mass of fluid per unit time, that's actually going through the surface. Okay. And you remember we drew a picture kind of like this, and we computed from that. And I think that's a really good exercise. Two really good exercises, actually, one for each of those scenarios. And I want to encourage everybody, if you haven't already done it, make sure that you're comfortable with why this formula for flux does what we claim that it does. And as always, come talk to me in office hours if you have any questions. Okay. So, big point, though, all of that assumed. Oh, yeah, question.
Does that normal vector has to be a unit vector as well?
One more time.
Does that normal vector has to be a unit
Yes,
vector?
that's right. That is one of the assumptions as we had it set up. Yep. So that calculation that we did back in chapter 3 assumed that you have a constant vector field on a flat surface, and we're now going to move along to considering a different scenario where you have a not flat surface, right? Some sort of curved surface, and furthermore, the vector field not constant, right? The vector field depends on where you are, and how do we deal with that? Well, look, what we do in this class, right? Pretty much everything we do in this class is we consider things, hard problems, that if you chop them up into little pieces, become easy problems, and then we add up over all of those little pieces, right? So we're going to do exactly that. We're going to consider one little piece at a time, and we're going to talk about how much flux there is through each little piece. And of course, each little piece is approximately flat. Sufficiently nice surface. It can be approximately flat. And it's such a small little piece that the vector field won't have much time to change. And so the vector field is approximately constant. So on that little piece, we can just immediately write down an answer, which is, here's that small piece, and here's the formula that we already had for how to answer the question on little small pieces like that. Flat surfaces, constant vector fields. Okay. All right, now I've glossed over an important problem, and that is when we say flux, which direction is the positive direction through the surface? So we talked about this back in chapter 3, but the normal vector, right, represents, helps us keep track of what the direction is that's perpendicular to the surface, but which of those two directions perpendicular to the surface it points tells us what we're going to consider to be the positive direction through the surface. Now you can see that in this little piece down here. If I choose this as my normal vector, and if I look at this flow of fluid like that, well, you can see that dot product's going to be positive. Said differently, this fluid is flowing the positive direction through the surface. So by virtue of this flux turning out to be positive, we can tell that we're talking about a flux in this direction through the surface, not in the other direction. Okay. All right. So in order, again, to make the question well posed, we need to have that decision made in advance. In other words, we can't just talk about a surface. We have to talk about an oriented surface. Right? So the oriented surface means it's not just a surface, it's a surface attached to this idea of which way is the positive direction. Is that cool? All right. So this is our first sign that something's actually pretty different here, right? That this is not the case when you're computing mass. This is not the case when you're talking about surface area. If I want to compute the surface area of that surface, there is no such thing as a positive direction. What do you mean direction through the... We're not going through the surface. I just want to compute the area of it, right? So the fact that there is an orientation in play makes it feel like this is a different kind of a situation. This is a scalar surface integral, probably not really quite getting its hands on what we're really dealing with here. So, in fact, let's write this all down and note that that works out as we are expecting. Whole is the sum of the parts. On any given little piece, like so, there's how we compute on the piece. Just plugging in. And now let's take a look at this expression right here. And at a casual glance, you might say, well, yeah, that looks like a scalar surface integral, because check it out. We have a scalar differential, and my integrand, in fact, is a scalar, right? And why I say this is actually different is in what we typically call a scalar surface integral, the integrand is a function of x, y, and z. It's a function of position. And here you can see it's more than that in this case. This integrand also depends on not just where that little piece of surface is, but how that little piece of surface is sort of arranged. You know, how is it sitting in space? And as indicated by this normal vector. Right? So this is really very much a different thing, and what I'm going to do now is going to ring some bells from chapter 6. I'm going to rewrite below this an analogous set of equations that we wrote down when we were computing work. Just give me a second to do this. Let's see, we had f dot t ds, and instead sometimes we like to write that as f dot dr. Okay, so you'll notice that structurally the way those equations are written down, I mean, you see the analogy vertically. And let's talk for a quick moment about the dr vector. What's the dr vector? What's its deal? Why do we like the dr vector? Well, it tells us two things. It tells us t and ds. Right? It tells us by its magnitude how big, how long is a little piece of curve that we're talking about. And it tells us by its direction, unit vector t, which direction that little piece of curve is oriented. So this dr vector, it has a direction and a magnitude that tell us both the orientation and the size. Everything that we should need to know about our piece of curve, all wrapped up in this one single thing called dr. Right? So we're going to do the same thing in the surface integral equations. Now, I'm going to take, let me do this in a different color. I'm going to take the n and the ds together. Again, orientation and size. Everything I might need to know about that little piece of surface, whatever little piece of surface we're interested in for this d phi. Orientation and size, that's all we need to know, and that we're going to call ds vector. So when you look at it by itself, I think it seems a little arbitrary, but once you see kind of in the opposite order, but I mean morally we kind of had the same arrangement, let's say, with line integrals back in chapter 6. So it's very, very analogous. It's very convenient notation, very natural notation, I think. And this is how I prefer to think of a vector surface. Whoa, sorry, what happened there? I navigated wrong. Okay, yeah, here we go. I don't know what happened there. So, this is how I prefer to think about a vector surface integral. And now you see why we call it a vector surface integral, because the differential is a vector and the integrand is a vector, visibly writing it this way. How we doing? Everybody all right with that? Okay, so how to compute these? And good news, we already know. We just have to realize that we already knew. Again, old news. We established this last time and revisited this earlier today. Right? If you have a parameterization, you have an input piece of area, output piece of area related by the stretching factor. We know how to compute it, blah, 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 all old news. And this is just a recopy from the previous page, what we literally just got through talking about. I just like to have it handy, so I recopied it down to here. And now, look how easy. I claim we already have what we need. This formula for ds as magnitude of capital N ds dt. Just stick it on in there like that, and we're basically done. There's one little rewrite that I'm going to do, kind of for computational convenience, I suppose. But I'm going to rewrite this like that. Do notice that I have an asterisk over here. I'm going to have to talk about this a little bit. But the case I'm going to make for now as to why this is okay is, let's think about what this capital N vector is. This capital N vector, it points in the direction perpendicular to the surface. Oh yeah, that's what little n is. And it has magnitude. Let's see, the magnitude of capital N is the magnitude of capital N. Oh, that's what this product's magnitude is also. So these two things that I have circled in purple, both, now this is the case I'm making for the moment, both point in the same direction, both have the same magnitude. Looks like a duck, quacks like a duck. Kind of feels like it ought to be a duck. Everybody see the case that I'm making there? Now again, asterisk. Okay, here's what the asterisk means. The asterisk is my confession that I've already committed a math crime. What I've said is not true. It's close. It's really close. But there is a subtle yet critical little mistake that I've made that I don't want to be distracted by for the moment. So we're going to go with this for the moment, and then in 3 minutes I'm going to come back and we're going to talk about what the problem is with it. This is mostly right, and the way that I'm going to apply this is going to be right, but we will have to fix this in a couple of minutes. Okay, so for the moment, if you want to compute a flux, here's how to pull back through a parameterization. Very handy formula. You should definitely make sure to know this. And here's the example. You can see I'm going to use that formula right there. And let's see, we have a vector field given, and we have a surface given. Let's see, it's a certain portion of that paraboloid, the portion sitting above the unit square. So we got a surface, we got a vector field. Let's compute the flux. Now, this formula says I'm going to need to know what capital N is. So I'm going to have to first parameterize, then take the appropriate partials, then take the cross product. That's going to be my capital N. So okay, let's think about those details. How did I parameterize here? Graph parameterization. Surface came to us as a graph. Graph parameterization is a convenient one in a lot of cases. Is that cool? Okay, we take the partials. That really is just computation. Hopefully, no big deal. Make sure you're comfortable with that. The cross product. You gotta do the whole. Anyway. It just did a couple of details. And we get this as our capital N cross product, and then as we just got through stating, we just plug that in, and it's pretty much all over at this point. Now I do have to plug in my vector field. My vector field is this, and I claim that my vector field then turns into this. Now what happened there? Where did that Z come from? Well, again, don't forget, if you want to know, for example, Z, the parameterization tells you. Parameterization is literally telling you X, Y, and Z as functions of your parameters. So that Z is S squared plus T squared. Is everybody with me? Is that everybody happy? Everybody satisfied? Okay, last thing we need to talk about, where do these bounds come from? So here's where you have to think about the geometry a little bit. Let's think carefully about our domain. Our domain is given let's see, I'm going to squeeze it in. You know what, let me do this in a different color. So our domain is, it says, above the unit square. So here's the unit square in the xy plane. We're looking for the portion of the paraboloid sitting above the unit square. So that's going to give me something that looks like that. This in purple is our surface. Let's see here. Let's talk about x and y on this surface. What's the ranges of values of x and y? Well, this surface literally is what comes from this unit square. X and y clearly range between 0 and 1. But don't forget, x and y are s and t. So if we know x and y go from 0 to 1, that tells us that s and t also go from 0 to 1. What do you think? Everybody good with that? Okay, so chapter 5, plug and chug. You multiply out this dot product, you get a great big polynomial. Easy to take anti-partials of polynomials. Plug in 0 and 1, 0 and 1. This is actually a pretty easy double integral, and it's just a matter of cranking it out. Okay. Everybody happy with this example? Okay, confession time. I have messed up, again, on purpose. I like to get one under our belts, get a win in the win column before we start thinking about subtleties. I've done this several times in the past, of course. Okay, the subtlety here is about orientations. And it was a subtle one. Let's think about how the parameterization might matter. When you parameterize, the purpose of a parameterization is to produce points on the surface. If you look back at all the methods that we talked about for how to create a parameterization, we came at it from the point of view of, I just want to be able to produce points that are on the surface. We're not really thinking about orientations. But the orientation kind of follows in this sense, so once you have your R, well, that determines these partials. Their cross product determines the capital N, and that capital N determines what we're going to call the parametrized unit normal, right? So when you create a parameterization, even though you don't realize it, when you create a parameterization, you are imposing an orientation on the question. You're imposing an orientation on the surface. Now, is it the correct orientation? Oh, wow. Why would it be? It's not clear why we would expect it to be correct. The question came to us with a given orientation, either that way or this way. Right? Again, keep in mind, if you're going to compute a flux, we need to have an oriented surface. Why would this orientation that followed out of a construction that I made up, why would that necessarily make the correct choice? Since this given orientation for the surface could go either way. Right? There's no reason to think that we would have guessed right. Everybody see the problem? Now this is subtle because very often we use lowercase n to refer to the parametrized unit normal. And we also use lowercase n to refer to the orientation unit normal. And so from a characters algebra type standpoint, it's really easy to mess up and think, oh, okay, well, let's see, we had an orientation unit normal, This, by the way, this is where I committed the math crime on the previous page, right? I turned this into this, and I put the asterisk there. So what we had at this stage was the orientation unit normal, and when I just replaced all of this with that, keeping in mind that that capital N vector has its own orientation, which is the parametrized unit normal. So when I did this one little step right here, right, looks like a duck, quacks like a duck, and all that, I was assuming that the parametrized unit normal that I created was the same as the orientation unit normal that I was given. And it's just not something you can assume. Does that make sense to everybody? All right, so this is annoying. Let me go back to back in chapter 6. So this is long back in early chapter 6, and we were talking about vector line integrals, and we made the observation that, well, look, you do have to parameterize the correct direction. If your curve is going this way and you parameterize that way, well, look, you're going the wrong direction. You're going to get the wrong answer, but in particular, you're going to be wrong by a minus sign. Right? So we're in exactly the same situation now. The good news is that even though we have the wrong answer, we're wrong by a very predictable amount, namely a minus sign, and I can just fix it by inserting a countering minus sign. It's actually pretty easy to fix. Okay, so that's good news. Okay, so let's see how this works in action. The hardest part of it is remembering to think about it. You just have to remember, oh yeah, I can parameterize however I want, but I've got to pause and remember, oh yeah, I've got to check and make sure the orientations are correct, and then if it's not correct, don't forget to insert that extra minus sign, right? So it's your responsibility, right? I cannot emphasize this enough. If the question comes to you well stated, namely with an orientation given to you, that's your cue that you have to make sure that you either parameterize correctly or that you account for it appropriately, one or the other. Okay, so here we go. All of this is exactly the same as what we saw in the previous example. But in the previous example, it was oriented upward. Now, why did I orient it upward in this previous example? Well, because I was trying to keep the secret for dramatic purposes, trying to de-emphasize the question of orientation. I wanted to deal with stuff like getting in and plugging in and the pulling back. I just wanted to get a win in the win column, right? But I made this upward oriented to be consistent with the parameterization that I was going to create, which you can see. It's got a positive z-coordinate, which means it's somewhat upward. So the orientation we ended up with conveniently is the same as the orientation we were supposed to do. I rigged up this example so we'd get lucky. All right, this next example is rigged up so we will not get lucky. And let's see how to deal with it when we don't get lucky. Okay, so we parameterize. Just however is most convenient. Don't worry about orientation at this stage. Just get those points on that surface. Get your parameterization. Compute the partials. Do the cross. And once you've got your capital N vector, whoops, I'm in the wrong color. Once you've got your capital N vector, now pause. And again, this is the hardest part, is remembering that once you compute your capital N, you have to pause and think about orientation. Now, we were given here a downward orientation in the statement of the question. It is our responsibility to compute downward flux. You look at my capital N, this is clearly not downward. This is upward-ish. Right? Of the two different options, only one of these could be reasonably called downward. And it's not the one that we have. Everybody see okay, so I've identified that we have a problem. Everybody see the problem? All right. So now how to fix it? Well, what we were going to do anyway is we were going to say that flux is computed with this formula. And now let's worry about orientations. The flux we were supposed to compute is supposed to be, let me zoom, we can see better. The flux we were supposed to compute is downward, so I'm going to color that one green. Rewriting it with a ds vector, let me remind you, the ds vector uses the given surface orientation. So those are oriented the same. And where we get the switch is when I start writing in terms of capital N. That has the wrong orientation. And likewise, the formula that I computed for N has the wrong orientation. So where do I insert the minus sign? The greens and the blues differ by a minus sign, so I fix these equations by inserting a minus sign right there. Does that make sense to everybody? And then just proceed with the calculation. Everything's fine after that. Okay. And of course, don't forget to carry along that minus sign. Okay, now here is a way to mess this up, and this is important. Keep in mind, and I know I say this a lot, but it's really important. It's not about answers; it's about your reasoning, right? We want to see, mathematically appropriate reasoning, right? And if you make a sign error, you have to fix it as you're making it. So let me point out now, how will it look? What kind of nonsense will we end up writing if we insert the minus sign in the wrong place? So let's pretend that I did not insert the minus sign here. And so no minus sign there. Let's suppose that I insert my minus sign here instead. Now, in terms of the final answer that you'll compute, doesn't matter. Again, not the point. That's not what we do here, right? So now let me just point out a couple of ridiculous things that are on the page, right? There are two ridiculous statements on the page right now. And here's the first one. That, claiming that that's equal to that is not true. The green orientation and the blue orientation are opposites of each other. These two things in the purple, those are negatives of each other. They are not equal. And that's not mathematically valid. You can't write down 5 equals negative 5. It's just not true. Does that make sense? Everybody see the problem? So the fact that I did not put the minus sign here means that this equation here does not follow. That's not mathematically legit. And it's worse than that, because now let's look at this equation. This says the blue orientation is the negative of the blue orientation. No, it's not. They're the same. So that is also wrong. Right? So we've got two sign errors here. Just by inserting the fix-it minus sign in the wrong spot, that equation is wrong and that equation is wrong. And this matters. I mean, this is, mathematically valid reasoning is part of what we do here. So be careful to fix it correctly. Yep.
Is it acceptable just to kind of identify that you've calculated the wrong n vector?
And then at the very end and say, by the way, I computed the wrong thing and therefore...
Before you even start doing this, just write the n vector actually equals the negative, and then you can.
I hear you. I totally hear you, but that's a problem in a different way. If you say, you know what, n equals, let's see, what did I call these? Okay. If I say, rs cross rt, and then if I say, okay, well, I'm just gonna put a minus sign there. But well, now my problem is, but that equation's not where these other equations came. Now you changed the whole framework, and now I don't know what anything on your page means. So that's actually a problem as well. I'm going to say you can't do that. Now what you could do is you could let's see here. Let me get rid of all these minus signs. Shoot, hang on. You could get rid of all of these minus signs and then say, equals ... and compute and get, let's say I don't know what the answer is here, but let's just suppose the answer is like 6 or something, right? And then say, wrong orientation implies that my actual, flux equals minus 6. Where's my equals? Equals minus 6. That would be reasonable. Yeah. That's what I thought you were asking. Yeah.
No. Would it be fine if you just use a slightly different symbol? You say n vector some 2 or star or something.
So we're going to get into. So you remember my complaint with the time travel arguments? It's not that it can't be fixed. It's that I don't know what you understand, right? And so what you I think our goal here should be to come up with what you can do to account for the problem at hand, but without creating confusion in what the grader is going to interpret from what they're reading on your paper. I think that would be more confusing. And I think you're going to get yourself into more trouble than you get yourself out of. So I wouldn't advise that myself. So I think you should either put the extra minus sign in the correct spot or do the full calculation wrong and then say, by the way, this whole calculation is wrong, and so the actual answer is this. Does that make sense? Yeah. Cool. Okay. All right, so let's talk about the language here. There are some little subtleties of the language. Let's look at this surface here, this paraboloid. On that paraboloid, there are 2 orientations. That's what I'm going to call the green orientation there, and what I'm going to call the blue orientation. Keep in mind, an orientation means which direction through the surface, or we're going to consider the positive direction through the surface. So green is one of the options. Blue is one of the options. How am I going to distinguish these from each other? A pretty good way to do it in this case is to use, let's see here, upward to describe the green one, downward to describe the blue one. And now let me complain about this. There is something uncomfortable about me using the word upward to describe that green orientation. If you were to overinterpret from what I mean by upward, you might interpret, upward means exactly, 001, right? Exactly straight up, which is not what this is doing, right? So the purpose of these terms, upward and downward, in this context is to distinguish between the 2 available options, right? N equals 001 pointing straight up is not even on the table. That's not even perpendicular to the surface. So that's not what that upward could possibly mean, right? So when we say upward or downward in a situation like that, we're just looking for ways that are unambiguous in distinguishing between the actual 2 options that exist. And notice these green vectors, all of them point at least somewhat upward and in no sense downward. Notice all these blue vectors point at least somewhat downward and in no sense upward. And so these terms, they're not exactly descriptive of the orientations, but they are unambiguous in which of the two actual candidates they refer to. Does that make sense to everybody? It's I'm going to say deliberately sloppy language so that we can address what we're trying to communicate. I'm trying to distinguish between two options. I'm not trying to tell you the formula for the normal vectors. So this is just kind of how we have to talk. I mean, I guess I'm open to other ideas about how I can casually, without the formula, refer to the green orientation specifically, right? I'm open to suggestions. I don't think we're going to do much better than what we have right here. So you just have to remember not to overinterpret from this. So I have seen the following on tests many times, by the way, that a student will see, some complicated surface and it'll say oriented upward, and the student then thinks, okay, my in vector then is 0, 0, 1. And that is absolutely wrong. It doesn't follow. It's not a reasonable interpretation of what was given. So please don't make that mistake. This is one of those things where the bigger a deal I make out of it, the less I see this kind of mistake on exams. So that's why I make a big deal out of it. Okay, now, importantly, we have to tailor the language to the circumstance. So let's look now at this surface. That surface there. And again, there are two orientations. I think it'll see better. Yeah, okay, let's do it like this. There's the green orientation through the surface, and then there's this blue orientation through the surface. Wouldn't make much sense to say upward and downward. The blue and the green orientations both have some vectors that are somewhat upward. And they both have some vectors that are somewhat downward. So upward and downward, they aren't unambiguous. Right? They don't resolve the choice between the two actual options. So that would be terrible language. If the perfect language for the paraboloid, it's unacceptably terrible language for the sphere. On the other hand, inward versus outward, fabulous. Right? No ambiguity. Perfectly clear what that means. Everybody see what I'm talking about? You got to tailor the language to the geometry of the circumstance. Questions? Okay, couple of little lucky bits of geometry. You may recall back in when we were talking about line integrals, we saw a couple of examples of really nice geometric good fortune. Right, and here, spheres are awesome, and we just happen to be able to deduce that F and DR are always orthogonal, and dot product 0. We walk away, problem solved. That kind of thing can come up in other circumstances. So here, again, we have a sphere centered at the origin. That immediately tells me that my position vector is perpendicular to the surface. Now that's a geometric insight. That's the nature of spheres centered at the origin. This is a peculiarity of spheres centered at the origin. Only spheres centered at the origin have this, but it remains that R vector is perpendicular to the surface. So if I want the unit vector perpendicular to the surface, all I have to do is normalize the R vector and check it out. Nice, handy, super easy formula for the unit normal vector there. That make sense? The heads up for stuff like this. Now, does this work to our advantage? Well, we happen to have been given the vector field here was that. In this case, this dot product happens to be exactly 0. And so, yeah, in this case, this was a big payoff. In general, it isn't necessarily. It may or may not. If the dot product had not worked out to be 0, if I had a function of x, y, and z that remained, I would have a scalar surface integral for which I would have to parameterize, right? So this sometimes, you can get clever with the geometry and trying to avoid having to parameterize and ending up, still having to parameterize. But on the other hand, sometimes you will get lucky and it saves you a bunch of trouble. Okay, let's see here. I think, may be out of time here. Let me just check. Yeah, we got 2 seconds. Call it a day. Drawing the line right here. Y'all have a good rest of your Monday. See you on Wednesday. Have a good one.